Hi, hello everyone, good morning. Welcome back to our virtual classes. Topic was capacitors. We did few examples last class, and one more time we will do more examples because capacitor happens to be a very popular topic. So let us try to cover some more models. Now here in this present session I would like to do on arrangement of plates, net capacity, arrangement of different dielectric slabs, finding net capacity. At the same time, on the networks of capacitors also few examples. Now, this first topic I am taking it as the system of plates, arrangement of plates and finding the capacity of the system. Now here you see, I have shown an arrangement of 1, 2, 3, 4, 5. I have shown arrangement of 5 plates, identical plates, each of surface area capital A, and separation between any two plates is D. The usual notations which we have used earlier, A for surface area, D for separation, 5 identical I have shown here. And now this is how they are arranged. This is how they are connected to potential points A and B. Now the question is, find the effective capacity across A. Now look here, for any such arrangement of plates that is given, we know that what is meant by a parallel plate capacitor, an arrangement in which two plates, parallel separation and PD created between them, right? Two plates with PD is essential point, right? If you allow that, now look at this point, and I'm giving number 1, 2, 3, 4, 5, right? 1, 3, 5 connected to the point A, and here 2 and 4 connected to the point B. Alternate plates. Now what do you observe? 1 and 2, two plates, parallel separation, and also PD between them. So similarly 2, 3, you will find PD, 3, 4, yes, and 4, 5. So here we find, for given 5 plates, we find 4 capacitors, right? How many capacitors? 4 capacitors, such that C1 equal to C2 equal to C3 equal to C4, and all of them same as C, and that C of course A epsilon naught by D. Now what is this specialty in the arrangement? You will find all they are arranged between common potential points. Remember our definition of parallel arrangement, common PD, connection between common potential points. So here you will find out of 5 plates we are getting 4 capacitors, each of same capacity, and the arrangement is parallel. That's what is parallel arrangement. Now each of them has a capacity of A epsilon naught by D. Now the effective capacity across AB, parallel combination, 4 identical. You remember n identical capacitors in parallel, we have said effective is n times C. The same here I have taken. So CAB is 4C, 4A epsilon naught by D. When you look at these numbers, one thing is very clear, you can generalize the result. Now here 5 plates, you got this as 4. Out of 5 plates you got 4 capacitors. So if it is in general n plates, you will have it as n minus 1 capacitors, and in this arrangement are all parallel, n minus 1 A epsilon naught by D will be the result. Right? This is what is the case of called variable capacitor also. Now here you will find the same type but with a small difference I am showing. Now here I have shown 4 plates, like, and the same cross section, same surface area capital A, and the separation between the plates happens to be D. Now here, the way it is connected to the potential points is shown difference. Now here you see, if I name them 1, 2, 3, 4, 1 and 4 connected to this potential VB, and the 2 and 3 connected to the potential VA. Therefore in this case, what we find is that 1 and 2, the arrangement with PD, yes, therefore the capacitor. 3 and 4 is also an arrangement with PD. So it's again a capacitor. We got 2 capacitors. But now look at these plates 2 and 3. Both 2 and 3 connected to same potential point A. No PD between the 2 and 3, therefore the arrangement does not act as capacitor. Therefore here in this case we have only two capacitor formation and each of capacity C, saying A epsilon naught by D, and now since they are in parallel, we are writing again C across AB, the effective capacity is 2 times A epsilon naught by D. So whenever arrangement of plates is given, we have to see whether there is a PD for the adjacent plates. That's the key point. Now, when you understood these two examples, I would like to do the same example with another type of connecting points, arrangement of plates, but with another small difference you will find in the next example. Look here, again shown 4 plates, but this time how they are connected to potential points. I have made 2 and 3 points connected to the potentials VA and VB. Now across AB, what will be the effective capacity of the arrangement of the system? Now in this case what you find is, of course 1 and 2 with a PD form a capacitor, 2, 3 also with a PD form a capacitor, 3, 4 also form a capacitor due to the PD. Now but what about the arrangements? What about the arrangement? Earlier we have seen in such case all of them are parallel. But now you draw the given circuit according to the given potential point. Now here, to make it clear, first I am showing you in terms of plates. The first plate and second plate, one capacitor. Second and third, you will find second. Second and third, one capacitor. 3 and also forming a capacitor. Now where is the PD? Between the plate 2 and 3. So between the plates 2 and 3, I am showing these A point and B point. Now what do you observe? When you look at this can be simplified as this 1, 2 and 3, 4. Therein, if I call them as C1, C2 and C3. Then if I show this arrangement as a small circuit, C1 and C3 series, yes, C1 and C3 series, and for that arrangement C2 will be parallel. Now these are the points A and B, because between the plates 2 and 3, right, what do you observe? C1 equal to C2, C1 equal to C3 equal to C. Therefore C and C in series, it will be, yes, C by 2, and of course C2 is also C because identical symmetric arrangement. Therefore what is the observe? C and C by 2 parallel arrangement. Therefore what is the final answer? Parallel means C1 plus C2, and therefore now in this case what is that? CAB is equal to C plus C by 2, 3C by 2, where of course A is, that C is C for A epsilon naught by D, capacity of each arrangement, like that. So in any case, even in the same example, supposing I have a change, hope you understood this, right? How this arrangement is converted into a small combination of capacitors I have shown. Now here, let me make a small change. A small change I am making. What is the change? Now let me change the points A and B. The potential points I am changing. Suppose this is how it is arranged. 1 and 3 connected by a wire. And now here, between the points 2 and 4, the potential points I have shown. Now you just go ahead, what will be the difference that you find in the previous case and this case. I just leave it as a homework for you. Any of your doubts, and if you want the answers, of course you are free to call your teachers and get the answer. So likewise, arrangement of plates and effective capacity is one such a very popular case for our NEET and CET. This type of examples based on the arrangement of capacitors with dielectrics, different ways in which number of dielectrics are placed between the space. Now First example you will see here, where plates arrangement, area A, I'm telling you, half of the space with constant K1 directly, another half with K2. Remember here it is equal thickness d by 2 and d by 2, but constants are defined K1 and K2. Now here what will be the effective capacity of this arrangement, and also what will be the effective dielectric constant, because we have used two dielectrics. If those two dielectrics are to be replaced by a single dielectric, what would be the dielectric constant of that single slab can also be a question. So for those answers, now here you see. Now what is the, you observe here, now you have this one forms a capacitor. A capacitor whose area is A and the thickness is d by 2, constant is K1. So shall I write C1 is equal to, it is completely filled, therefore K1 times A epsilon naught by d by 2. Simple expression for capacity, right? Now what will be that of C2? C2 is also, see here, same thickness d by 2, but the constant is K2, complete filling, right? So it is K2 times A epsilon naught, same area for both, and thickness is also same for both, but it is d by 2 for each. Now what do you observe here? Here we observe that for this arrangement, what is that you observe? No division of charge, no splitting of charge. No splitting of the charge. A common charge among the capacitors is the series combination. You remember, right? Therefore now here C1 and C2 are two capacitors and they are in series. They are in series. Therefore what will be the effective constant, effective capacity will be C1 C2 by C1 plus C2. C1 C2 by C1 plus C2. Of course this A epsilon naught by d by 2 is a common term. You please simplify this. What will be the result I am writing you? It will be 2 K1 K2 by K1 plus K2 times A epsilon naught by d. Do it for yourself. The rule is C1 C2 by C1 plus C2. You have expressions. Get the simplification. 2 K1 K2 by K1 plus K2 A epsilon naught by d. Now this 2 K1 K2 by K1 plus K2 will be the effective dielectric constant. Right? That is how. But in the same example, supposing the other way, like here we have taken K1, K2, same thickness, each half d by 2 and d by 2. But here look at same example with a small change. What is that? Here I have taken K1 and K2 but of different thickness T1 and T2. Again it is complete filling is there and the difference is unequal thickness. For this case, again the rule is the same. You have to write C1, you have to write, then you will be K epsilon naught, A epsilon naught by T1, and again K2, A epsilon naught by T2. Again that will give you as C1 C2 by C1 plus C2. So for this case I am writing the result. What is C effective? You will get the result A epsilon naught by T1 by K1 plus T2 by K2 will be the result. Same way, no difference whatsoever. Here you got 2 K1 K2 by K1 plus K2 and this 2 term and everything is because of this d by 2 term. But here thickness is different. This will be the result that you get. Supposing even if it is 3 slabs or any slabs, the same result will follow T1 by K1 plus T2 by K2 plus T3 by K3. So whatever number of terms that are given, you will take that way. This one. Now another arrangement I have shown here. In the next figure what you will find is, again, earlier it was same cross section A but thickness d by 2 each. But look in this example, thickness is same for both but it is half and the other half of the space filled with dielectric of K1 and K2. So here also you will get two capacitors, each of thickness D but area A by 2. Therefore, here C1 is equal to C2 is equal to, no, not equal to, I'm sorry, C1 is equal to K1 times A by 2 epsilon naught by D, and C2 is K2 times A by 2 epsilon naught by D. And now in this case, what do you observe? Now we are calculating the effective capacity, right? So look at this. What is that you observe? This capacitor C1 between the points A and B, and another capacitor C2 that is formed is also between the same points A and B. Now in this case, it is common potential points, which is the basis for, yes, parallel combination. Therefore, now in this case, C1 and C2 are in parallel. They are in parallel. Therefore, what will be the C effective? C effective is, yes, C1 plus C2. Add these to A by 2 epsilon naught by D is the common term, right? Therefore, what do you observe? K1 plus K2 by 2 times A epsilon naught by D. 2 I have written here. Why? Because now the effective dielectric constant of the arrangement will be K1 plus K2 by 2, like this. So supposing if it is 3 or any other number, the same will follow the rule. First you have to write the capacitors that are possible in the arrangement and see whether they are in series or parallel combination and get your results. And the same, just now I will draw some of the arrangements and hopefully you will do it on your own. Let me have small changes here. So now you see I have shown an arrangement like this. This is an arrangement. This is an arrangement exactly half. I am writing it as D by 2 and D by 2. Here what is that? This is K1, this half, this is what is A by 2, and the second half, the lower half I am showing it as K2, and this one is what is K3. Now for this arrangement, what will be the case? Clearly you will find that arrangement has 3 capacitors. How? This one is a capacity. I am writing it as C1 for K1 dielectric as C1 is equal to K1. What is the area? Yes, A by 2 epsilon naught by distance is D by 2. So these 2 terms will cancel. And similarly, what is that C2 for the dielectric K2? I am writing it as K2 times. This one is also A by 2 epsilon naught by D by 2. Got it? Now what is this arrangement? Between them it is common potential points, therefore they are in parallel. C1, C2 are in parallel combination. And now what about C3? C3 is equal to K3 times, yes, K3 times area A epsilon naught and the distance term is D by 2. Now complete arrangement, what is that you observe? Now here this is nothing but C1 and C2, C1 and C2 parallel, and for that combination C3 will be in series. So final answer is C1 C2 by C1 plus C2 is this combination. I will write here. So what is that you observe? C1 C2 by C1 plus C2. One arrangement, sorry, C1 plus C2 is one arrangement for parallel, and the other one is C3, and they are in series. So what will be the effective capacity? Yes, 2 capacity series combination. Therefore it is C1 plus C2 into C3 by C1 plus C2 plus C3. So that is how you will. So any other change also, the key points is write all the different possible capacities and identify whether they are series or parallel, and you can get the effective capacity. Few examples on the network of capacitors that are given. First example, I have arranged 1, 2, 3, 4, 5, 6, 7, 8, all 8 capacitors identical. Each of capacity C is the data. So this is the arrangement. All 8 capacitors identical. Capacity of each of them is C. Supposing already have used the word C naught, different light remains C naught, whatever the symbol, right? Now this arrangement, we are asked to find again effective capacity of the network. But whenever you are finding the effective capacity, the important thing is the open terminals. Now the question is asked, first question I am asking, what is the effective capacity across the terminals AB? Please carefully watch the figure A point and B point. About that, now I want the effective capacity. Now let us see. When I consider these points A and B, that is battery is connected across A and B. That's what is the meaning of that. Now in such case what happens? Now you see I am now rewriting this for AB. When it is across AB, what do you observe? This capacitor and this capacitor, because this is where you have connected a battery, suppose, then what happens? These two capacitors will be not included in the network. That is no charge or no PD for these capacitors. And therefore, we will neglect these two. Not neglect, they are not included in the circuit. Therefore, I can rewrite the circuit as, now can you see? When I have taken these two, yes, this is the system you get. Now here, between A and B, you just watch the network one more time. And what is that here observe? This is C, C and C. You see no division of charge. No division of charge. Therefore, all these three capacitors are in series. Right? In a classroom, we have given a very loose analogy. You will consider them as a pipes and splitting of water. Supposing here, this is same pipe going, no splitting of water, right? Similarly, now here, no division of charge, no splitting of charge, or series. Therefore, C, 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 the answer will be C by 3. And therefore, now, what will be the final picture that it looks like? Now, this is case. C, C. This one is C and this one is C by 3. So C and C by 3 now the parallel combination. Therefore, now you can see C and C by 3 are parallel combination. If we take it, C plus C by 3 parallel combination, therefore it is 4C by 3. 4C by 3. So now it is what is A and B. Across A and B, now you have 3 capacitors. How? C, 4C by 3 and C, you will find the answer. As you remember that expression? For 3 capacitors, you can straight away use C1, C2, C3 by C1, C2 plus C2, C3 plus C3, C1, likewise I have given the result. Otherwise, C and C series, answer is C by 2. C by 2 and 4C by 3, they become series. Like that also you can see, now you can write C1, C2 by C1 plus C2. C1 value is C by 2, C2 value is 4C by 3. And what the answer you get is CAB is equal to 4C by 11. 4C by 11. So that is how we have calculated the effective capacity across given open terminals. Now I ask you to change the open terminal. Supposing instead of AB, if I ask you across A and C in the same figure, if I ask you to find A and C, then what happens? You tell me again. These two, because if it is connected across A and C, these two capacitors will be in open circuit, no charge or no PD across them. Therefore, again, what result you will get is the same result you will see. The same type of result you will see even across A and C. Therefore, in this case, C across AB effective capacity is same as effective capacity across A and C also, and it is equal to 4C by 11. Now, in the second case, what I have taken is, see, now here I am calculating C across the terminals AD. Now you will find battery across AD. Battery across AD. Then what happens? When battery is across A and B, this one and this one, look at here. These two will be in open circuit, right? When it is battery across AD, no charge, no PD for these two. Therefore, now this is the consequence. You will find 1, 2, 3, 4, 5, 6 only now here. And then now in this case, what do you observe? Now when you are following from A to D, these two are in series. Therefore, C and C in series, C by 2. Again, these two you will find as C and C in series. This one is also C by 2. And these two are in parallel between these 2 points, say common PD. C by 2 because of C and C series. Again, this C and C series, C by 2. Again, this C by 2 and C by 2 parallel. Therefore, what is that you get? Now, this is the result you get. This is C by 2, C by 2 parallel. Add, we will get C again. So, this is point A and B. So, what will be C effective across AD? It will be C by 3. C by 3. Now, supposing you are asked to compare C across AB and C across AD. Earlier we told CAB and CAC are same. Whereas now CAD compared with CAB, any such examples you can extend it, whether it is CAD higher value or CAB higher value, the same question can be changed with a small difference. Hope you have understood this. Next example also, network of capacitors. Here I have shown 5 capacitors, identical capacitors, each of C. They are arranged in the form of an English alphabet A. It's in the form of English alphabet. Find the effective capacity across. These are the open terminals A and B I have taken. Now once again, when you are finding the effective constant between the open terminals, follow the open terminals. When I follow the open terminals from A to B, what is that you observe? You will observe that this C and C, topmost capacitors, no division of charge, no splitting of charge you will observe. Therefore, those two become series. C and C series, you will get C by 2. So, 5 becomes 4. That's what I have shown here. See here, C and C and C, and this one is C by 2. So, 5 has become 4. 4 becomes 3. So, likewise, successive deduction will go on. This is one such example that I have shown. Now here, C by 2 and C parallel. Therefore, now this is C plus C by 2 becomes 3C by 2. So, 3 capacitors. 4 becomes 3. You can say C, 3C by 2 and C. Now you can further reduce as C and C, C by 2. C by 2 and 3C by 2. They become series. So, that is what is I have written. So, what is the final answer? C by 2 into 3C by 2 by C by 2 plus 3C by 2. That's what is your answer. Alright. Now, I have formed the example in such a way that sometimes this is what happens. We don't read the questions properly, and even though we got the answer, we could not get the scoring there in the exam. See, example says C across AB. C across AB is given as 1.2 microfarad. Now find the value of C. Now here, what is the answer here you get? This is 3C by 4 by 2. Right? So its answer is 3C by 8. Now the answer is not 3C by 8. 3C by 8 is given to be 1.2 microfarad. Therefore the value of C is, this is 0.4. 4 yes. So this is 0.32. Right? This is 4 times. This is 0.4 times. Right? Therefore it is 8 into 0.4. It is 3.2 into 10 minus 6 farad microfarad. 3.2 microfarad is the answer. Like that. So this is a successive deduction method where the number gradually decreasing. One such example. Even next example also for the practice that I have shown. Again, successive deduction. Now look at the second circuit. look at the second circuit. Do remember, in the examination, more network with more and more number of capacitors, the example will be simpler. Based on symmetry, we'll get very, very easy answers. Or successive methods, we'll get easy methods. Now, this example you will find, there are two types of capacitors that is shown as a kind of ladder you can find here. Now, all these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, all these are C1. One type of one value given to be 3 microfarad, and these C2, 1, 2, 3, 4, like that, they all have one magnitude of 2 microfarad. Now the answer is, what is C, A, B? As I have told you, successive reductions happen. Now where to start or where to begin with? What you will find that everywhere you will find division, splitting of charge. But now come to this last part. These 1, 2, 3 capacitors, you don't find division of splitting of charges. Therefore, C1, C1, C1 all are in series. So what will be the effective capacity? Now it becomes C1 by 3. In the given example I have said C1 is equal to 3 microfarad. Therefore 3, 3, 3 in series. The resultant will be 1 microfarad that you get. Therefore now if I eliminate this, what is the number that I get? This is 1 microfarad. What is the value of C2 that is given? 2 microfarad. See here, this is 2 microfarad and 1 microfarad. Now you will see between the common potential points. Therefore again 2 and 1 parallel. 2 plus 1 becomes 3. We are successively reducing it. Therefore now when you remove this again becomes 3. Again 3, 3, 3. Got the point? Got the point? The same will now follow. Again 3, 3, 3, 1. This becomes 1 and 2, 3. That will follow. So what is the final network that you can show? This is what you can show. 3, 3, 3 across A and B. Rather, in fact, it is C1. This is C2. And this one is, what is 3 microfarad? You got it. So now C1 in C2, sorry, this one is also C1, right? Now 3, 3, 3. So final answer is C, A, B equal to, right? Series combination, identical. Therefore answer is 3 by 3. 1 microfarad is the answer. Successive reduction method. Same successive reduction, but in slightly different way that I have shown. So look at this example. This time also I have shown a ladder which is infinite ladder. First you will see one capacitor, all are identical, of course. In this case also, these are the open terminals, he says, right? One capacitor, again 2 identical. Next row you will find as 4, next row 8, next row 16, so on. So likewise, this is a ladder that is given, and finally this is what is infinity, you can say. This is the ladder that is given. Now we have to find the PD across, effective capacity across A and B. What is that here? You see this is C. 2 capacitors in series, C by 2. Therefore, this is C. Next one is, yes, 2 capacitors in series, C by 2. Next one is, yes, you are right, C by 4. Next comes C by 8, so on. This will be again infinite series, infinite ladder. But what you find is that again all these, first one is C, C by 2, C by 4, C by 5. All of them have common potential points. So this is an infinite ladder with C, C by 2, C by 4, C by 8 and so on in parallel. So what will be the effective here I am writing? C across AB is equal to, yes, C plus C by 2 plus C by 4 plus so on infinite. Your high school mathematical skills will tell you that this is an infinite summation in which the terms are in GP. You can see that, right? In GP, what is that common ratio? C, 1 by 2. Again 1 by 2 into 1 by 2, 1 by 4, 1 by 4 into 1 by 2, 1 by. So this is an infinite summation of GP, and you know that what is that result? A by 1 minus R. Hope you all remember this. A for the first member, R for common ratio. So first member is C by 1 minus 1 by 2. So the answer is 2C. So again, this was an infinite ladder, and we got net capacity as not infinity, but the answer is 2C. Next one, I will take one more infinite ladder, but see the difference. What is that small change that we bring in the next example? See, one more infinite ladder. Earlier you have seen that one on the board. Now this is another infinite ladder. Infinite ladder, you will see all these capacitors 1 microfarad, and these middle are given as the same number 2 microfarad each. Infinite ladder. Now for this case, the solution will be different. Here you don't get that regular series and parallel combination, therefore it cannot be deduced. It cannot be deduced in steps, and that is why the solution is different. Let us suppose that I will take, let the effective capacity across AB be C, some number I have taken. Let C AB be C. Now, in this infinite ladder, what you find is, I can take this 1 microfarad and 2 microfarad as one unit. This is 1 unit of a ladder. 1 unit of a ladder. Now this is the effective capacity of the infinite ladder. Now for an infinite ladder, remember, if I add one more unit, then also that will have the same capacity. C is the principle here. Because already it was an effective for infinite ladder. For that infinity, if you add one more, no difference whatsoever is the principle. And that is why here I am showing the deduced final network as the effective capacity was taken to be C. Now we are adding one more unit like this 1 microfarad, 2 microfarad, this as one unit we have added. Now this is the result is now C across AB is again C. As we have told, for infinite ladder, add one more unit, no change. Now this case also CAB is equal to C. But what do you observe here? You will observe that this C and 2 parallel combination, and for that this 1 microfarad is in series. Therefore, the final answer, this one is, yes, this one is 1 microfarad, and this one is 2 plus C, the parallel combination. This is AB. Now we have two capacitors C1 and C2. Therefore now I am writing CAB as 1 into 2 plus C1 C2 by C1 plus C2, same as C. Got it? Now here you will get a quadratic equation on the simplification. Generally I don't do all these simplifications and all in the classroom. I leave it to you. Even I wish to do the same. Just one more line I will show, and I will write the quadratic equation here. What is that? This is 3 plus C into C. So this is 3C plus C square is equal to 2 plus C. So final equation is C square plus 2C minus 2 is equal to 0. Is that okay? Now it is in the form AX square plus BX plus C is equal to 0. A quadratic in X, here there is quadratic in C. A for 1, B for 2, C for minus 2. Now you can deduce the roots. Among those roots, one you will get as positive, the other one you will get as negative. Remove the, you leave the negative term that you get, the positive term will be your answer. So this is for infinite ladder. In the previous example, supposing different capacitors are shown, instead if all the capacitors in the infinite ladder are same, I have taken them as C0 each. So what will be the answer? You will do the same method, same final quadratic expression that you get, and the answer I have just deduced it and I am showing it to you. CAB is equal to root 5 by 2 times C0 for this way. You see, all identical capacitors forming an infinite ladder. Okay. One more interesting case in the case of capacitor networks. Here we use one principle. Look at the given circuit diagram. We have shown a total of 7 capacitors identical and between open terminals A, B. Now the question is, find effective capacity across AB. Now, you find one very important thing when I ask you to see that this entire network, supposing if you draw one line, why only particularly at that line? Because now what you will find is that when I draw such imaginary line, you will find the total figure as the mirror images. Now both sides, the LHS and RHS sides, you will find them as mirror images. One is the mirror image of the other. So that is what is the specialty in this network. Please do remember, all the given capacitors are identical and symmetry is there, do remember. And also the imaginary line where I have drawn, you see, yes, it is passing through the point of symmetry. That is the key point. When you do that, if you find it as a symmetry point, then what it does mean that we can ignore this contact. We can ignore that point of contact through which we have drawn an imaginary line for the mirror image. If I remove now this one, this contact I will remove, then this is what is the network that changes. Now this becomes easier, which can be done in the deduction method, successive reduction method. Now see, after removing this point of contact, this is what is that we get. C and C series, again parallel with C. And of course our regular reduction method now will continue, right? So when is that we are applying this method? When you find symmetry number 1 and number 5, all identical capacitors, and you find that point of symmetry is, contact is is discordant. After that you will find a circuit where it will be again successive reduction method. Now you see here the same C and C, C by 2 and C parallel, therefore it is C plus C by 2, 3C by 2. This one C, C. Again you will see here C and C, series part, therefore it is C by 2. And finally you have C, 3C, C. This one is again you can say C by 2, C and C, 3C by 2. And this one is C by 2. And already we have shown in the last previous example only, this will give you as 3C by 8 and parallel combination is C by 2. So 3C by 8 plus C by 2, yes, 7C by 8. So that is the system of symmetry, remember. Next example also a very simplest one, but actually that is called as, what is called as shorting, short circuit. Such example now I will show you 1 or 2. Now in this case, these are 4 capacitors that I have shown. 4 capacitors, 2C, 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 identical I have shown, need not be any number, and this one is 12C. And the question says, CAB is not asked actually. No, he says CAB, the effective capacity is 2.4 microfarad. Find the value of C. Find the value of 2C or find the value of 12C. Whenever you are reading the question, you never take it for granted. Read the question thoroughly and full. Okay. Now in this case, what you observe? Look at this point, which is nothing but a point A. You will find that there is a connection from this capacitor, from this plate. Also you will find from this plate the second capacitor. Also you will find the same from the third capacitor also. So what is that you observe? This point A now is a common potential point for these 3 capacitors. Common potential point. Similarly, look at this point. If I call the point as some P. Now P will be, look at this, from this plate you have a connection, and from these two plates also you have a connection to P. So P also a common potential for all the three capacitors. What does it mean? These three capacitors between common potential points, therefore between A and P, these three are parallel. These three are parallel. This is what is A, and this is what is P. This is 2C, 2C, 2C. It becomes a parallel combination, and of course afterwards it is 12C. It is 12C is the point B. 2C, 2C, 2C. You will get it as 6C, and this one is 12C. Now successive reduction. Now it is now series combination of 6C and 12C. 6 into 12 by 6 plus 12 into C, given to be 2.4 microfarad. Right? This one is, you will get it as 4C is equal to 2.4. This one is 72 by 18, right? 4C is equal to 2.4 microfarad, and therefore C is equal to 0.6 microfarad. Therefore now you can calculate the capacity of any of them. So here in this method of shorting, though the arrangement you see ones side by side, generally we have a misconception that side by side series combination. Now this time it is not a series combination, rather it becomes parallel combination. Right. Now the same kind of what we call short circuiting. One more example I would like to show here, and what difference that you will find. Let us see what difference you find. Now in that I have shown about 4 capacitors, and I have all of them taken as identical. This one is V0 1, 2, 3 and 4, where this capacitor is with a key. It is with a key. A key is across this C. That's what is that. Now the question is that what is the change in the capacity when the key is open? When the key is open, that is initially key is closed, and now if the key is open, what will be the change? Or else initially the key is open, and after closing the key, what will be the change in the capacity? Either it can be change in the capacity, or it can also be change in energy stored in the system. Anything such question can be asked for you, right? See here, supposing I take initially key is open. Initially key is open. In such case, yes, what is the network? This one is C and C parallel. This becomes 2C, 2C and this one C. They are in series. So 2C and C. Whole it will come it as a 2C by 3 for the series combination C1, C2 by C1 plus C2. C and C, 2C, and this one C in series, C1, C2 by C1 plus C2 will give you 2C by 3. And for that, this C will be parallel, because common potential points it becomes for these two branches, this becomes common potential point. Therefore, 2C by 3 plus C, that is 5C by 3 is the resultant capacity when the key is open. Because I show you the circuit one more time. So this is what is the circuit that you get. Yes, this is what is the circuit that you get, and effective is 5C by 3. Now key is closed. Key is closed means key is across this capacitor C, you can find, right? Therefore, when this is closed, these two plates PD becomes 0, and that is why we say this capacitor is short circuited. What is the meaning of short circuit? Short circuit means, okay, let me change the key here. Suppose here I show the key. Yeah. Yes. Right. Supposing now key is closed. When key is closed, this capacitor will be short circuited. That is, it won't work, no charge or no PD created across this one. Therefore, then this circuit simply becomes the two capacitors in the upper branch parallel, followed by one more capacitor in series, and this will be the circuit that we get, because this is short circuited. It will not be in the working condition. Earlier I have shown one key, and why I have removed, because if that gets short circuited, the entire circuit will be disconnected from battery, and that is why I have removed that and I have shown this. So this capacitor is ineffective. Therefore now it is C and C. Answer will be 2C by 3, because this is 2C plus and 2C and C in series. Therefore it is answer is 2C by 3. So 5C by 3 becoming 2C by 3. What is the change that happened? If that change is asked in terms of percentage, what is that? So 5C by 3 minus 2C by 3, answer is yes. Answer is C. Answer is C. What does it mean by C? I am writing, suppose initially if this is what is C1 and now this is what is C2. Now what is C1 difference C2? It may either increase or decrease. In our present example it has decreased. C1 difference C2 is equal to C. C1 difference C is equal to C. And now what is the percentage? Always remember how to get the percentage of change. Delta X by X into 100. Delta X by X into 100 is the getting the percentage change. So initially it was 5C by 3, right? Answer C by 5C by 3 into 100. So that will come around 60%. Like that. So short circuit is another principle to remember in solving. What is meant by short circuit is shown in the figure. Watch it carefully. So these were a few models that we have covered. Yesterday's class and today's class completely for solving some models on capacitors. Remember, one more time, a reminder for you that we are sharing you good number of assignments with ranging models. These are only few models that are discussed in the classroom, but we are sharing large number of models through assignments, and I hope you are following those assignments and doing them, and more and more calls from you is also expected. Good day all of you.